Hello, I'm Soke from Facility Management Division of Okinawa City Waterworks Bureau. This is my fourth year working for the Bureau. For the first 3 years, I was in charge of water quality testing for the water we distribute to the city. From April 2020, I transferred to leakage prevention section, and now my main focus at work is to reduce water leaks. Today, I'd like to introduce the distribution block system, which is one of the early detection measures for water leaks. Without further ado, let me start. I'll be using PowerPoint slides from now. First, let me explain what the distribution block is. These diagrams show the map of water distribution pipes in Okinawa City. We have 100% service coverage in the city, and the black lines represent the pipes installed throughout the city. On the right, you see that the pipe network is divided into small sections. Each of these color-coded sections represents what we call a distribution block, which is created by dividing the network with valves or other means for easy management. The use of those blocks is advantageous on 3 points. First, it enables improved operation and maintenance by identifying the amount of water distributed as well as leaked. Second, by organizing water flow, it helps minimize pipe damage from disaster or accidents, as well as repair work required. Third, it enables water pressure management per block. Achieving proper water pressure for each block helps reduce water leak. As you will see, creating distribution blocks has facilitated many areas of our work. Now, let me explain benefits of distribution blocks in detail. First, data obtained from flow meters enables effective leak detection. Flow meters are installed at the inflow point of each distribution block to measure the amount of water distributed. Leakage in a block can be estimated by comparing the inflow with the sum of customer consumption within the block, obtained from meters installed at each household. In addition, installing meters with communication functions, such as electromagnetic type, enables monitoring of daily flow trends, with real-time data transmitted from communication equipment. Second, organizing water flow by establishing distribution blocks helps minimize supply interruptions for leak repair work and burst and other negative impacts from natural disaster. It also enables to minimize affected area from accidents and to take prompt initial response in case of emergency. Moreover, establishing distribution blocks facilitates water supply with appropriate pressure. With 120 meters of difference in elevation within the city, ensuring proper water pressure has been a big challenge. Areas with high elevation tend to have low water flow problems due to low water pressure, whereas lowland areas tend to have excessive water pressure that causes bursts and eventually increases leak from the damaged pipe. By controlling pressure with pressure-reducing valves and other necessary equipment in distribution blocks at areas with high elevation, we strive to maintain water pipes and reduce water leaks. This is how we started our leak prevention activities. Let me explain how we calculate distributed amount and leak. First, let me start with a case without distribution blocks. In this diagram, 25 households are supplied from a service reservoir. Let's say the reservoir supplies 1000 cubic meters, and the sum of meter readings from each household is 850 cubic meters. Then, the amount of water leak is 150 cubic meters, and the effective water ratio is 85%. To locate where the 150 cubic meters of water is leaking from, we would have to conduct leak detection in the entire area shown on the diagram. With such a wide area, it will be a huge challenge. What happens then if we establish distribution blocks in the area? Now, block meters or DMA meters are installed at 4 points, and we've established 4 distribution blocks. The metered value from block 1 is 200 cubic meters. 100 cubic meters from block 2, 200 cubic meters from block 3, and 500 cubic meters from block 4. That gives us 1000 cubic meters in total. As it is the same as the distributed amount from service reservoir, we know there is no leak from the reservoir to the block meters. Next, we compare the value we took from the block meters with the sum total of meter readings from households within each block. This tells us that there's 20 cubic meters of leak in block 1, no leak in block 2, 30 cubic meters leak in block 3, and 100 cubic meters leak in block 4. We now know the amount of leak from each block. By prioritizing the blocks with higher leaks, we can conduct leak detection efficiently. Once we locate leaks, prompt repair work is important. Distribution blocks help us minimize the impact of accidents as well. This diagram shows the service reservoir supplying to 5 blocks and locations of water valves. Let me explain how we respond to an accident near the block B inlet, for example. By closing 2 valves installed on the inlet, we can stop the leak. However, by doing so, we also stopped water supply for the entire block B. Then, to provide backup supply from block A to block B, we open normally closed isolation valves. Supplying water from block A helps minimize the affected area from the accident. As you can see, thanks to distribution blocks, we can effectively deal with leak accident with appropriate valve operations. Distribution blocks facilitate equalization of water pressure as well. Let's say we establish distribution blocks in an area where a service reservoir located at an elevation of 100 meters supplies to lower areas until 20 meters of elevation. First, water pressure is measured at each altitude. We then divide the area by altitude into distribution blocks so that water pressure within each block is equal. Now, each block has equal water pressure within itself, but the pressure differs greatly among those blocks depending on altitude, from 0.2 megapascal to 0.8 megapascal. Excessive pressure can cause leaks. Therefore, installing pressure-reducing valves at block inlet is necessary so that water is supplied at appropriate pressure. Let's say appropriate pressure here is 0.2 megapascal. Installing pressure-reducing valves achieved equal pressure of 0.2 megapascal for every block. As you can see, establishing distribution blocks helps reduce water leak by adjusting excessive water pressure. Since water pressure and topography are closely related, good understanding of local topography is crucial in designing distribution blocks. There are 5 things to bear in mind in establishing distribution blocks. First, blocks should basically be established by dividing areas by altitude. It is to ensure the same water pressure within the block. Second point is flow direction and valve location. Direction of water flow needs to be checked, and the possibility of establishing a block by closing existing valves should be examined. Installation of additional valves may be necessary. Third point is pressure measurement at highest and lowest point in the block. Change in water pressure before and after setting up a distribution block needs to be checked. We should also be mindful of height difference, therefore pressure difference within the block, as it tends to happen in the case of a large block. Fourth point is water quality. It is our responsibility to always ensure that customers can use tap water with safety and ease of mind. Therefore, when we establish distribution blocks, we should pay attention to designate isolation valves with minimum stagnant water. If water stagnates, residual chlorine decays and worsens water quality. Fifth point is installation of block meter and pressure-reducing valves when necessary. Installing a block meter, a flow meter installed at inlet, enables measurement of distributed amount to the block. Comparing the amount with the sum of meter readings of customer consumption tells us the amount of water leak within the block. When pressure turned out to be excessive, pressure-reducing valves are installed to ensure proper pressure. Now, let me explain with a real case study of establishing a distribution block in Okinawa City. This is Awase first meter block, which we have set up recently. The block has 1,246 service taps with total pipe length of 18 kilometers. It has an area of 0.51 square kilometers and is located at a flat coastal area with little height difference. This is the pipe network that shows existing distribution pipes with black lines and valves with red dots. We then examined the possibility of establishing a distribution block like this. In designing a distribution block, we first identified potential inlet mains. The distribution pipe with 250 mm in diameter, the largest diameter in the area, was selected. It is located where you see a red arrow in the diagram. With both the network plan and on-site survey, we then assessed whether some existing valves can be closed to serve as isolation valves. We confirmed that establishing a block was possible by closing 9 valves. We then measured pressure within the block for 24 hours after closing isolation valves. The lowest pressure was 0.21 megapascal, which was within the appropriate pressure range, and therefore installation of pressure-reducing valves was unnecessary. The last step was to install a 200 mm nominal diameter electromagnetic flow meter. The meter enabled us to measure the inflow and minimum night flow. After the block was established, we found that inflow was 1,400 cubic meters, minimum night flow was 15 cubic meters per hour, and average revenue water rate was 98.73%. Now, let me give you the overview of distribution block system in Okinawa City. According to our annual statistical report of 2019, the number of population served was 142,533. Average daily water supply was 49,441 cubic meters. Total pipe length was 577.986 kilometers. And the number of service taps was 49,140. Meanwhile, the number of service reservoir was 6. The number of distribution block was 48, and effective water rate was 94.98%. Okinawa City receives treated water supplied by the Okinawa Prefectural Enterprise Bureau at 6 branching points in the city. 2 of these points exclusively supply water to the U.S. bases, so civilian areas of the city receive water supply from 4 remaining branch points. In the Okinawa City distribution block system, civilian areas are divided into 4 large blocks. Each of the branching points has a 300 mm to 600 mm nominal diameter meter. The meters tell us how much water is distributed to each of the large blocks. Large blocks are divided into middle blocks. As you can see, middle blocks are mostly set up for each service reservoir. Electromagnetic flow meters are installed at service reservoirs, so we can get distributed amount for each of the middle block as well. Then, medium blocks are divided into small blocks. Moreover, small blocks are further divided into micro blocks. Altogether, there are 48 blocks in the city's block system. We keep track of the distributed amount, pressure, and flow route in each block. These photos show the manhole to a block meter chamber located at the inflow point of a distribution block and an electromagnetic flow meter installed inside. Inside of the chamber, there is a pit or a working space with a 200 mm nominal diameter electromagnetic flow meter and a 200 mm nominal diameter pressure reducing valve. This is the pressure reducing valve. Pressure data is obtained with a pressure sensor and is transmitted to the Waterworks Bureau office. This is the ground plan of pressure reducing valve chamber. The chamber is 3.2 meters in length and 1.4 meters in width. Blue arrows show the flow route. With a bypass pipe, supply doesn't need to be interrupted at the time of valve or meter replacement. These photos are taken at the time of pressure reducing valve overhaul. Currently, there are 28 pressure reducing valves that are in operation. And we conduct periodic inspection as well as overhaul whenever necessary. Isolation valves, which are normally closed and isolate the block from others, are painted yellow for easy identification. There are 300 of them in the city. They are very important for managing distribution blocks. When we conduct leak survey, we first check to see if they are closed properly. Meanwhile, block meter is also installed inside, but sometimes they get submerged underwater depending on location or weather condition. It doesn't affect meter function, but we sometimes drain the chamber to maintain optimal meter condition. Along with distribution blocks, Okinawa City has also established a metering system. By utilizing radio wave used for mobile phone network for data transmission, the Waterworks Bureau obtains data from 37 block meters in the city and pressure sensors via the internet. Real-time data on distributed amount and water pressure is therefore available to us. We have a meeting each morning with real-time data on distributed amount and water pressure from the metering system. What we go over for each distribution block include data on pressure, trend of distributed amount and minimum night flow, and leak instant. If abnormality is found, we promptly look for the cause. The distribution block metering system enables minimum night flow analysis. To analyze, we check the flow trend from midnight to 6 in the morning, during which consumption drops with less human activities. If the value increases, leakage is suspected. Based on accumulated data for each block, we have set reference values for judgment. This table shows each distribution block's minimum night flow between June 13th to July 3rd in 2016. The values in black are normal values, and those in red are abnormal values. Let's take block number 1 for example. The minimum night flow on June 16th was 10 cubic meters per hour. Since the increase in value from the previous day suggested leak, we conducted detection work and repaired the leak found. After the repair, minimum night flow went back to normal from June 30th. We use a computerized billing system to calculate water bills. This screen displays customer information. By comparing the sum of each household's consumption and each distribution block's inflow measured with a block meter, this system calculates revenue water rate automatically. The name of a distribution block, which this customer meter belongs, is displayed here as attribute information. We utilize Geographic Information System, or GIS, to manage location information of isolation valves, block meters, and pressure-reducing valves. Location of each household's meter and service pipes, as well as pipe type and diameter of distribution mains and laterals, installation year, and detailed plan can also be displayed. Pipes with frequent bursts and aging pipes can be identified. So conducting leak survey on these priorities enables efficient detection and improved detection rate. Red triangles show locations of past bursts. Data on accident date, cause, measures taken are also stored. Pipes with frequent leak incidents are prioritized for early replacement. Information from the distribution block meter reading system, billing system, and GIS are centrally controlled. Such centralized control has been very useful in keeping track of facility data, leak detection planning, improving response to emergency and accidents, and information sharing. Lastly, let me show you transition of revenue water rate to see how effective block system has been. We started establishing the system back in 1996, and data utilization started in 2000. The use of data from the blocks has been helpful for narrowing down a target area for leak detection. You can see significant improvement in the graph after the introduction of distribution block system. That concludes my presentation on the distribution block system. I hope you found it useful for stable waterworks management in your country. Thank you.